Hello, well, I'm here today to show you a Python project I've been working on that involves hiding secret messages within a computer image. Now, just to give an overview of what this demo will include, we'll be discussing steganography, the structure of a computer image, and how we can hide and retrieve text within said image, followed by a demonstration of the project. Now, first thing we have to discuss is steganography. Now, what is steganography? It is the practice of hiding information from unwanted eyes. And while this may seem a completely new concept to some of you watching this, this technique has actually been used in the times of ancient Greece, where Hexadecimal, the ruler of Miletus, would tattoo a message on the shaved head of a slave and let their hair grow long enough to be sent to his son-in-law Aristogoras, who would then shave the servant once more, revealing the secret message with it. Now, while the computer age has revolutionized the way we can hide messages, this technique is still used in the computing world on mediums such as files, videos, and, for the sake of this demo, images. Which brings us to the question of how can we even get into how can we actually store a message on a computer image? Well, this is where we have to discuss the structure of a computer image. Now, an image online is simply a collection of pixels comprised of three bytes of data, red, green, and blue, with a fourth byte of data, a fourth data byte for transparency called alpha. These values can be expressed in hexadecimal form from 0 through 9 and A through F, meaning 10 through 15. It's off of base 16 of hexadecimal. And what these bytes of data do is that they make up the colors that you see on an image. And as far as what we can do with steganography is that we can use the least significant bytes of data with these pixels and replace the least significant bit of these bytes of data with a binary 1 or 0. Now, just to give a more crystal clear picture of what I'm talking about, let's just take this color blue right here and look at the equivalent hexadecimal value of it. So you would see this little blue dot within hundreds upon thousands of pixels of any computer image you would see. So we're looking at this very, very close up. And now, the way that they're structured, these pixels are structured, is that we follow, it goes red, green, blue. So the value of the red pixels in this case would be 24, green pixels would be 76, and then the blue pixels would be E4 in this case. Now, when I mentioned the least significant bit of a pixel, what I was getting at is that we could take the original color here, this 24, 76, E4, and change either the least significant bit of the red, green, or blue. Now, for instance, this is changing 24 to 21, 76 to 71, E4 to E1, and you may notice that the color changes in some cases drastically, others maybe not so much. But just keep this back in perspective. This is one of thousands contained in a single image. So unless you're really looking well, you're not going to see this change unless you're looking very close up like we are right now. So now that we've covered how the image is altered when we store this message, it's important that we discuss how the message is created and then stored in there. So part of what my program does is that it'll ask you to enter in an ASCII message, and then it will convert it into the binary equivalent. This binary message is then added to a delimiter binary string to be able to retrieve the hidden message later on. Now, might be a lot to take in, but just for right now, let's just focus on what's happening here. So let's just say I enter in hello world, and this is its binary output. And then let's just say we set the delimiter to these 4 ones and 1 0. So then when we create the binary message, we take this line of binary, excuse me, and then tack on the delimiter binary to create our binary message that we see here, 1 0 1 0, followed by the 4 ones and the 1 0 of our delimiter. So then we take that binary message and then we ask the user which type of pixel you would like to store this message into for the image. Now, this is more of a general overview, but let's just, for the sake of this example, I'm going to access the least significant bits of the red pixels. So if we were to look at what it was originally, you would see in this case this 24 for this pixel, for the red pixels of this pixel was changed to 21. Just following it down, you see how this 24 turned into 20. This 33 right here turned into 31, 48 for this pixel, change into 40, etc., until we reach the final end of our binary message. And then once that's done, we can simply hide the message, and then the pixel, and we don't tamper with the pixels from there on. So now that's great. We've hidden the message, and then let's just say we send it on to our friend here, and then they would ask themselves, okay, I got the image, now how do I retrieve the message? Well, so what it would do then is actually look through the pixels here and look for any under a specific color. So let's just say if I told the person we were looking at the red pixels, they would look at the least significant bits of said red pixels and then extract them, and then as you're going through the image, and then test to see if the last 5 digits of the binary message is equivalent to our delimiter binary string that we established earlier. And if it is, just wait 1 minute. Okay, here we go. So what would happen then is that if the last 5 digits of the binary message is equivalent to 11110, we would then decode everything up until the delimiter for the original message. So in this case, if I were to simply decode 1010, it would be equal to hello world. Now we have the message that was hidden in the pixels, and then we're able to retrieve it. So now that I've gone over hiding, retrieving, and most importantly, creating the message, it is time to go over, or really just show you the demo. So let me just mosey on over here. Ignore the cute doggos. That's not what I wanted to open. Here it is. Okay, so I've already ran this program a few times already, but just for the sake of how it works for you, the viewers here, um, here is the name of the program right here. Then you'll notice this -E option. And then here is the image that we are going to be looking at. So if I were to pull up my pictures folder, this will be what we are going to be storing the message in. I know it works because that's what I tested it with. So one thing I want to mention before we encode a message is that if you were to take a look at this image and go into properties, you would see right here the current size, not the size on disk, the current size of it is equivalent to 1,290,757 bytes. So I am going to simply copy this value, put it on Notepad, so current size is equal to that amount of bytes. So when we store a message, you will see this value change, either increased or decrease. Either way, it will more than likely not be this same exact value. So minimize that, close that, minimize that. So on to actually running the program. So first thing you'll be asked is, which type of pixels do you want to hide your message in? So you have an option of 1 for red, 2 for green, 3 for blue. So I'm going to choose blue. I can actually turn on numlock. Here we go. Okay, blue. All right, so I chose option 3. So enter a message to hide. So this is where we are. This is where we could create or enter in hello world, as I described in the demo. Hello world, 10/3/2020. Of course, I put the wrong. Let's just change that for the sake of being clear here. Just gonna put some, I don't know, other text, just really change the size of the image here. So there we go. So now it's completed. And if we were to run the same command as before, instead of the -E, we use -D. We will then be able to retrieve said message from this image. But before we do that, let me just pull up that image again, see if the size had changed. So, okay. So you'll notice here under size, we have now 1,290,906 bytes. So let's make this altered size equal to 906 instead of 757. So we know something has been changed to this image. We know that the size has been altered here. So if we were to go back to this program and run the -D option instead of -E, we would be prompted to ask which type of pixel you previously chose to hide your message in. So then I chose blue, so I'm going to choose option 3 here. And then, okay, chose option 3, success, hello world, October 3rd, 2020, and then all that. So, okay, I showed you shows you here that we selected blue, we enter this message in, and then when we retrieve it, selecting blue again, we have the same exact message that we put in. Now, for some of you, it might be fine, but for those of you who are really wondering what's going on behind the hood here, we can just mosey on over to my GitHub page for this Python program. So for the sake of how it works, we're just going to go from the bottom here. So if name is equal to main, run the main function. So let's just scroll up to here. Oh, here we are. So here we are in main. So in this little block of code, we see our parsers, or the part of code that allows us to run -e as a command, which will then go to our hide function, or -d to go to our retrieve function. So let's just run this as if we just ran the -e option. So here we first have to see if the options.hide is not equal to none. So what this is asking is, did we run the -e option? If that's the case, we ask the user which type of pixel you want to hide your message in. Once that's done, we then ask them to enter a message to hide. And then once that input is also entered, we send 3 things to the hide function as we print it out to the user right here. So the options.hide will be the image that you want to hide the image in. So in this case, it will be this picture of these cute doggos here. The text, this is your super secret message, followed by your pixel choice, red, green, or blue. So then we will then move over to the hide function. No, that's retrieve. So here we are, the hide function. We have 3 inputs: file name, the image, message, your hidden message, and then pixel choice. So first thing we do is we open up the image to be able to access the pixels. Once that's done, we then set our binary message right here using the string to bin function to take said message and convert it into binary, and then we tack on our delimiter of, in this case, 15 ones and 1 0. So if we just scroll up to string to bin, we then take the message and essentially take each part of the ASCII text, and then convert it into the equivalent binary, and then return it back to the hide function to then tack on the delimiter binary string here. So once that's done, we test to see if the image mode is in RGBA format, and if it is, we then convert said image to RGBA just for good measure, and then right below it, we then store the actual data of said image into the data as variable right here, followed by a open variable called new data. We set a variable for digit equal to 0, and then we create this variable temp as a blank string. So what we then do is that we go through the entire image pretty much stored in data here and test to see if the current digit is less than the length of the binary message. So this is essentially your message tacked on with the delimiter. So, so if this proves true, we then set this variable called newpix, the output of, let's see, first RGB to hex, where we take the current items, I should say, of 0, 1, and 2, think red, green, and blue, and then get the equivalent hexadecimal form to then send it to the encode function along with the current binary digits, so either a 1 or a 0, as well as the pixel choice to the encode function. So let's see, where did we put encode? Okay, so here we are in it, encode. So we have the hex code. This is your current hexadecimal value that we discussed earlier, the current binary digit, as well as your pixel choice. So just below, we have 3 hard-coded variables: blue equal to 3, green equal to 2, red equal to 1. So let's just say I chose to do pixel choice was blue. So what it would do is that look at the very first value of the hex code and see if the least significant bit of the blue pixel is equal to 0, 1, 2, 3, 4, or 5. So if that does return true, we simply assign hex code. We look at everything except for the first digit of hex code and assign either the binary 1 or 0 here. And once that's done, we return it to the newpix variable back into the hide function. But let's just say we chose to do green. Now, what we would do is that we would look at the third digit of the hex code and then see if it also ends in 0, 1, 2, 3, or 5. But one thing you have to keep in mind here is that you have to also save some pixels along the way, because what would happen is that you would have to first assign the least significant bit of the green pixels and then tack on the saved ones, just so that the actual structure of the hexadecimal value is still intact. You're just converting the LSB of the green to either a binary 1 or 0. So once you save these pixels and then change the green here in this case, you then tack on the tampered pixels along with the saved one. Now in the case of green, we are simply saving the red and green, and we're getting rid of the blue. I'm sorry, no, we're saving the blue in this case, because if you were to go it from left to right, it's red, green, blue. So we are saving the blue pixels for under save pixels if we chose green. And then down below, we have tampered pixels. This is where we are setting the least significant bit of the green to the equivalent 1 or 0. And then we take the tampered pixel, i.e. the new red and green, and then tack on the blue just to save the actual structure of the hexadecimal value. And then return that to newpix as well. And the same thing applies with red, only we're looking at close to the end of, I should say, beginning of the hexadecimal value, and seeing if it's between 0 and 5. And here we are saving not only the blue pixels, but also the green as well. And then we're altering the least significant bit of the red here and adding the equivalent binary. And just like the last one, putting them both back together just so the original value is saved. But in the case that the least significant bit of either blue, green, or red is not equal, or I'm sorry, is not between 0 and 5, we simply return none to the new pix variable and just move on to the next current pixel in the data's array. So let's just say, so if we just go back to the hide function, here we are. So let's just say we were given none, like we didn't find a required value of the least significant bit of either red, green, or blue. What we would do then is simply append the current pixel back to the data's array and just simply go back through the items here of this array, or I'm sorry, for this for loop, and then go back into the if digits less than binary. We would then go, we would look at this new pix and then go back to the encode function for the second one just to see if there was a desired least significant bit that we are looking to store the current digit of our binary message. So let's just say we actually got one and we have now a new tampered pixel that we want to append to our new data array here. So in this case, what we would do is then store the output to the red, green, and blue variables here, RGB, and then send the new pix to the hex to RGB. Why am I drawing a blank here? Function. That's what I meant to say, function. So let's just quickly look that up, see what's going on there. So hex to RGB. So here we have the equivalent hex code, or it should be RGB, or new pix, I should say. And then we strip away the, hold on. Oh, my bad. Here we are. So RGB to hex. Sorry, no. Hex RGB. What am I talking about? Okay, so we simply get rid of the pound sign, and then we convert it back to base 16, and then we return the RGB values of 0, i.e. red, 1, green, 2, blue in this case. So if we go back to the hide, so then we, after that's done, we take the new data array and append the red, green, blue, as well as the add in the alpha value for it as well, and then add that to the new data's array. And after that, we increment the digit by 1 so that we can then store the next 1 or 0 of the binary message. So once we go through the entire length of the binary message, we then test to see if digit is less than the full message. So if this proves false, we go then to the else statement, where we simply just store all the pixels back to the new data array. Simply, like, this is just essentially like we're done looking at the individual pixels. We're done testing to see if we can store another bit. We're just simply putting everything back where it was. And so once we go through all that in the for loop, once we go through each item in the data's array, we simply save it to the image, save it with the same file name, and then return the message completed. So this is, okay, we've stored the message, here it is, this is the pixels that they're into, okay, now we're done. So if we were to go back to the main function, and assuming the user had already run it again, but instead of the dash E, we go to dash D, we would then be going to the retrieve function. So here we are testing if, let's see, so if options, so first thing we do is see if, okay, was the options, was the encode function, or I'm sorry, the hide option used? No. Okay, so this proves false. So then we scroll on down to this one where it says, was the retrieve option used? Yes. Okay, so that was proof true. Then we go down to choose which type of pixel you chose previously to hide your message. And so this is where you would select the number. This is where you select the pixel that you stored your message in. And then once that's done, we simply print out the results of sending the image and your pixel choice to the retrieve function. So let's just see, here's retrieve. Excuse me. So what we, similar to the hide function, we take the image, we open it, excuse me, and then we create this binary string to an empty string. Excuse me, oh my gosh. So now we test to see if the image mode is in RGBA format. And if it is, we simply convert it to RGBA for good measure, and then using the data's variable again, data's being only to the retrieve function, not the hide function, we simply access the pixels of said image again, and then loop through each item in data's, and then for each item, we assign the value of digit equal to the output of sending item 0, 1 through 2 to the RGB to hex. And so what this does is that it will find the equivalent hexadecimal value and send that output to, along with pixel choice, to the decode function. So RGB to hex first, and then we'll go to decode. So here we are taking 3 inputs, red, green, and blue, and returning their equivalent hexadecimal value. And then we send that to the, decode function, where we take the hex code along with the pixel choice and test to see if you selected blue, i.e. 3, green 2, red 1. Very similar to the encode, but just opposite. Well, in this case, we are looking at the least significant bit of blue, green, or red, and seeing if it ends in 0 or 1. So if it does, we then return just the actual least just the actual 1 or 0 back to the digit variable, and then in the retrieve function, or if it doesn't, we simply return none. So let's just scroll back to retrieve here. So in the case that digit was equal to none, we simply pass by. So now what we're looking for, we move on to the next one. So let's just say if digit was equal to none, we simply say, okay, this proved true, we're going to ignore the else. So then we would go back to this for loop and then move on to the next group of items here and then decode the equivalent hexadecimal with your pixel choice. And let's just say we got a hit, we got a 1 or a 0, and then we would go right here, say if digit is equal to none, do this, but we're going to say that proves false, so we would go to the else statement, where we would then take the binary variable and assign it to the value of digit in this current time, and assign it to the current value of binary. Then we would test to see if the last 16 characters are equivalent to our delimiter string that I had mentioned earlier. So simply we would just iterate this all the way through until our binary string is equal to 15 ones and 1 0. So once we get a match here, after iterating all the way through datas, we would return the output of binary to string, the binary message excluding the last 16 ones and zeros. And that is where we would take the binary message and print out the equivalent message that you originally put in. So here is the binary to string function. So first we remove the binary format and then convert it back into the original ASCII text, and then we return the display message, what you see on the display, back to the retrieve, if I can find that again, and say, okay, now we're going to return this to the screen. Here's the message you hit it in. And so once that iterate, so in case we don't find anything in the decode function under this for loop right here, we simply say, we just simply return the string that we were given, and then once that is done, or if let's say the image we check to see is in RGBA mode, we would return a message that says incorrect image mode, couldn't retrieve message. So that pretty much wraps up this project. I hope you enjoyed it.